Chapter 12, Inventory Management. For this session, you will learn about ABC analysis and how it is used to manage inventory. You will learn about the economic order quantity EOQ model for matching inventory with demand. As part of EOQ, you will understand the inventory reorder point and safety stock. Finally, we will cover the link between inventory and customer service levels. To be successful, Amazon has become a leader in inventory management. Amazon started without inventory but evolved to add warehouses across the country. These warehouses are efficient and heavily automated. Order processing at Amazon is highly automated, starting with online orders, technology-assisted picking, packing, labeling, and shipping. Like many elements of operations, the goal is to minimize inventory while meeting customer service goals in alignment with the overall organization's strategy. Inventory accounts for up to 50% of total capital investment for some companies. Customer service is a function of inventory cost. Holding greater amounts of inventory improves the chances for increased customer service, but also increased costs. The inverse is also true. On-hand inventory provides a selection of goods for customers when demand fluctuates. Inventory is also used to decouple parts of the process that are not in full alignment. Inventory helps remediate bottlenecks. Inventory allows us to take advantage of quantity discounts and hedge against inflation. The top two examples of inventory facilitate customer selection, while the bottom two examples support the production process. Here are the most common types of inventory. Raw materials include screws, steel bars, and paint in a component manufacturing facility. Work in process includes partially assembled cars, while finished goods are ready for the customer, like the food on the shelf at the grocery store. MRO inventory is used to support the process, like machine parts, office supplies, tools, etc. This diagram shows the flow of inventory from raw materials through finished goods. We see that the vast majority of the time is spent prior to actual production. Since inventory can make up such a large cost for an operation, it is important that inventory be effectively managed. Accurate inventory data is used to perform an ABC analysis. ABC analysis groups items based on their annual dollar volume. Class A items have the highest dollar volume, Class C the lowest, and Class B in between. We use the ABC analysis to focus our attention on the most critical parts. The distribution of items between the three classes generally follows the 80-20 rule, with 80% by dollar falling into the A class, with the B and C items making up the other 20% of dollars spent on inventory. In this example, A items make up 80% of the dollars spent, but account for only 15% of the items. The exact proportions do not have to be 80-20, but this is a good rule of thumb. Here is a more detailed analysis where annual dollar volume is the product of annual unit volume and individual unit cost. Sorting in descending order, the top two items out of 10 account for 72% of the cost. The next three items are classified as B items with 23% of annual cost. The final 5 items, the C's, make up 5% of the total annual cost. Clearly, management attention should be focused on the top 2 items. Dollar volume is not the only reason to identify an item as Class A. Hard to find components, those with quality issues, and those with pending engineering change may also receive special attention. Management focus on A items may result in greater supplier development, tighter forecasting, and better inventory control. To effectively manage inventory records, accuracy is critical. Your analysis is only as good as your data. Regular verification of inventory may be necessary. Two-bin systems, cycle counting, and continuous tracking supported by automated methods may be used especially for A items. In order to ensure accurate counts, incoming and outgoing movement must be tracked and stockrooms secured. These steps will improve the accuracy of your inventory data and thus your management decisions regarding inventory. Cycle counting is the process of manually counting items on hand to verify inventory level. Cycle counting, if used, would typically focus on the A items and the B items to a lesser extent. The goal of cycle counting is to eliminate stockouts through greater inventory accuracy and facilitate improvement efforts. Here's an example of a cycle counting plan. Notice the ABC analysis of inventoried items and the greater frequency of review for the higher priority items. On the other hand, service inventories can be critical to success as well. Similar techniques may be applied, but there is often greater emphasis on personnel and control of material receipt and disbursement. We start by defining demand types. Independent demand is not tied to other items in inventory. Think of customer demand for finished goods. Dependent demand is tied to the demand of another item in inventory. Think of 4 tires of dependent demand for every car independent demand that is purchased. There are several costs associated with inventory. Holding cost, or carrying cost, is due to the storage of the item. Think of warehouse space, shelving, lift trucks, and personnel. Ordering cost occurs every time an item is ordered from a supplier. Finally, setup cost is a manufacturing cost incurred every time the factory sets up to make a certain item. Setup cost is usually proportional to the setup time. Here is a breakdown of the elements of holding cost. We see that overall carrying cost is 26% of the inventory cost. In this example, $100 of inventory attracts $26 of holding cost. We can see why we want to minimize the amount of inventory on hand. This data is simply an example. Holding costs vary widely based upon the items, industry, and desired service levels. The costs typically vary from 15% to as high as 40%. To achieve the proper balance and lowest costs, we analyze our independent demand to determine how much material to purchase based upon setup, ordering, and carrying costs. This is the EOQ, or economic order quantity. We will also look at the production order quantity, POQ model, and the quantity discount model. The basic EOQ model has several assumptions that are not always applicable in real life, but act as a starting point. Demand must be defined and constant with a known lead time for purchased items. Once delivered, inventory is immediately available. Here we see the expected sawtooth model of inventory quantity in stock over time. When new material, quantity Q, is received, inventory jumps up to that level. Inventory is gradually used at a constant rate until fully depleted. The average inventory on hand is simply Q divided by 2. Recalling our earlier discussion on costs, we see that setup/order cost per unit drops as the quantity increases. At the same time, the holding cost goes up as the inventory held goes up. Combining the holding cost and setup cost, we get a total cost curve that dips in the middle. The lowest point represents the optimal order quantity and the minimal cost. To minimize our costs, we order the quantity Q star each time an order is placed. Summarizing our EOQ cost analysis, we see that minimal total cost occurs when the holding cost and setup cost for a given quantity are equal. Ordering more or fewer items than Q star will increase total cost. Let's look at the EOQ equation. We start by defining the equation for annual setup cost. The variable definitions are listed here. Notice that the length of time considered for each variable value must be the same. We look at annual demand and annual carrying cost. If our starting point uses differing lengths of time, one or the other must be converted. Annual setup cost equals the annual demand divided by the quantity per order times the setup cost per order. Now we calculate the annual holding cost, which equals the order quantity divided by 2 times the holding cost per unit per year. We determined earlier that the lowest cost is found when setup cost equals holding cost. Equating the equations of the two costs, then solving for Q star, we find that the economic order quantity, Q star, equals the square root of the quantity 2 times the annual demand times the setup cost divided by the annual holding cost. For this example, we substitute the values into the equation and find an economic order quantity of 200 units. This will be the quantity ordered each time. Note that the demand and holding cost are annualized. Based on the previous calculation and the resulting economic order quantity of 200 units, we want to determine how many orders will be placed annually. This equation is the number of orders N equals the annual demand D divided by the economic order quantity Q star. Substituting the known values, we determine that 5 orders will be placed each year. Now we find the time between orders. The equation has the time between orders T equal to the number of working days per year divided by the number of orders. For this example, we assume 250 working days per year. This is 5 days a week over 50 weeks. The result shows 50 days between orders. Finally, for the same example, we determine the total annual cost, which we recall is the sum of the setup cost and the holding cost. Again, substituting the values into the equation for setup cost and then holding cost, we get $50 of setup cost and $50 of holding cost for a total annual cost of $100. In real life, your results are unlikely to come out to such perfectly round numbers, but the analytical process is the same. While not perfect, the EOQ model works well even in an imperfect world. Since the curve is relatively flat near the EOQ point, slight variations will have a minimal impact, making the EOQ results a good starting point for managing inventory. Now we move to the reorder point. The EOQ tells us how much to order, while the reorder point, or ROP, tells the team when to order the next quantity of material from the supplier. For this calculation, we need to know the lead time L, how long after placing the order the material will be received. The reorder point calculation is demand per day times the lead time in days. Note here again that the time frame must be the same. Both values must be in terms of days. The equation may also be expressed as ROP equals annual demand D divided by the number of working days per year times the lead time in days. Graphically, we can look at our sawtooth consumption model discussed earlier. We see that we back up from the needed delivery date when we run out of material. This is the date when the order must be placed based upon the lead time L. Moving up to the curve, the reorder point is found. When inventory drops to the reorder point, the next order must be placed. Applying the reorder point analysis to an example, we start by defining the problem and identifying the values of the variables. Given an annual demand of 8,000 phones over 250 working days per year, we can calculate the reorder point if we have a lead time of 3 or 4 days. For 3 days, we find a reorder point of 96 units, while a lead time of 4 days gives us 128 units. This ends our look at the economic order quantity model. The production order quantity model is used when inventory increases over time. Instead of receiving a shipment of material from a supplier, we create the product internally. As each item is produced, it is moved to stock. As a result, instead of the sawtooth model of the economic order quantity with a vertical spike of inventory when received, the inventory goes up gradually as replenished. For the blue portions of the curve, we are producing product and adding to inventory while drawing out material to fulfill customer orders. During the yellow portion of the curve, we have finished producing materials and are only drawing stock from the warehouse as needed. Lowercase t indicates the time while we are in production. Now we look at the situation where quantity discounts are available from the supplier. In this example, the base price is $100 per unit. However, if we buy from 120 to 1,499 units, the price drops to $98 per unit. Similarly, order quantities in excess of 1,500 units are at a $96 price per unit. We need to decide if we minimize our costs by taking advantage of these price breaks. The calculation for quantity discount model is shown here. We have added the cost of product to the setup and holding costs. Also note that the holding cost is expressed as a percentage of the unit price rather than a fixed cost per item. We see the slightly modified economic order quantity Q star equation. To analyze the value of a quantity discount, we start by calculating the economic order quantity for each of the pricing levels. Next, we determine whether the quantity exists within the valid range for that price discount. This will become clear when we look at the analysis graphically. Looking at the graph, we see three different total price curves, one for each pricing level: no discount, discount 1, and discount 2. Looking at the top curve, representing no discount, the EOQ falls above the quantity of 120 units. But this is outside of the applicable range, so this is not the answer. For this curve, the lowest cost point is when the curve crosses the 120 quantity vertical line. So the lowest cost quantity given no discounts is 120 units. Moving down to the next curve for discount 1, the EOQ falls within the valid range. So the EOQ for discount 1 results in an annual cost of $517,155. This is the best result so far. Finally, we look at the total cost curve for discount 2. Again, the EOQ falls outside the valid range, and the lowest point of the curve is at the border when it crosses the 1,500 unit vertical. At this point, the total cost is $520,053. Comparing the results from the three curves, we see that the lowest total cost is $517,155, implementing discount 1. All of the methods can be customized to meet specific business needs. Options include discounts for all units, discounts above a threshold, discounts on aggregate demand, and truckload discounts. Next, we review probabilistic models and safety stock. When demand is not certain, we use safety stock to avoid stockouts and maintain a certain service level. The revised reorder point equation is shown here. The difference is that we have added safety stock, SS, to the daily demand multiplied by the lead time. The goal is to minimize inventory while ensuring that the operation does not run out of material while waiting for the next supplier order to arrive. In this case, we establish a range from the minimum to the maximum demand during lead time while waiting for the material to arrive.